I will be presenting our paper PoseSonic 3D upper body pose estimation through egocentric acoustic sensing on smart glasses. Before delving into the details of our system, first let me show you the video demo of our PoseSonic system. We are tracking upper body pose using acoustic signal. Here you see in the left part of this frame that we are tracking the acoustic signal to track upper body pose. And we will discuss the detail of the system in later slides. So in this cool session, after seeing previous mocap papers, now I feel that I would have cited those interesting papers, but now I just got to know that. I hope I will cite that in my future works, and also hope that you will cite my works in future. So if we take a look into the contemporary pose estimation systems, we see that there are dedicated motion capture hardwares like Vicon or OptiTrack, and depth-based sensing system like Kinect. Although these systems provide very precise motion capture for full body pose tracking, but they come with a few caveats. First, they're very expensive. They're immobile, and they cannot work under the condition of occlusion, and most importantly, they're privacy invasive. On the other hand, researchers also worked on wearable-based pose estimation systems. If we take a look into the first work listed here, it utilizes IMUs on commodity devices such as smartwatches or smartphones or earbuds. And in the second work listed here, it uses camera mounted on a wristband to track human body pose. However, generally these systems require multiple instrumentation points, and particularly for camera-based systems, they're privacy invasive and consume pretty high power. In response to this, we propose PoseSonic, which is an active acoustic sensing-based upper body pose estimation system. Our system is a low cost and low power. The whole sensing system of PoseSonic costs less than $20, and with its very low power signature, it can last up to 21 hours with a battery equivalent to Google Glass. Our system is user independent, which means that it can maintain consistent performance without training data from the new user. And with our minimally obtrusive off-the-shelf eyeglasses form factor, we can track the upper body pose of the user, preserving their privacy because we don't need to use any sort of camera input or audible frequency range. So let's take a look at the PoseSonic form factor. So we put pair of speaker and mics on the hinges of eyeglasses, and here you see the zoomed in version in the right part of the slide. So this is a user wearing these eyeglasses, and the speakers emits ultrasonic FMCW wave, and this wave gets reflected on different upper body parts. This reflection is captured through the mics co-located with the speakers. After we receive the echo from different upper body parts, we move to our signal processing pipeline, which is first applying a bandpass filter on the received signal, followed by a cross-correlation operation on transmitted signal and received signal. The output of this cross-correlation operation is called echo profile, which is used as the input to our customized deep learning framework. Let's take a closer look into the echo profile. So the temporal axis is on the x-axis, and the y-axis from top to bottom denotes the distance from the sensing system. Let's go through an example to understand the properties of our sensing system. So here you see that the user is moving their right hand, and we can observe the movement pattern in the right channel of the echo profile. Conversely, when the user is moving their left hand, it's the same scenario. And this is intuitive that for both our movement, we capture it on both channels. And the most important feature of our sensing system is the user independence. So PoseSonic does not rely on tracking the shape of the upper body limbs, rather it tracks the trajectory of movement pattern. That is why you see that these two users have different physical characteristics, but as they are performing very similar upper body gesture, the echo profile, the acoustic echo profile captures very similar movement pattern, and it facilitates the machine learning model to work in a user agnostic fashion. Let's take a look at our deep learning framework. So we design a deep learning framework with cross-modal supervision. Here, the teacher network takes synchronized RGB frames as input and provide supervisory signal to the student network. The student network takes acoustic echo profile that I discussed previously as input, and with its ResNet 18-based deep learning pipeline, it predicts the upper body pose. We conducted 2 user studies. In our first in-lab user study with 12 participants, each participant participated for 90 minutes. And we collected data in 5 different indoor scenarios, which is shown here. And the participants remounted between each sessions to mimic the real-world usage scenario. We do extensive evaluation of our system, which is detailed in our paper. But if we try to summarize this, PoseSonic achieves 6.17 centimeter of mean per joint position error in a user-independent setting with a battery life of 21 hours. If we try to compare it with other pose estimation methods, we can see that its performance is pretty much comparable with any camera-based systems and better than IMU-based systems. And if you take a look at the user independence, PoseSonic is the only one system that can offer you user independence. And as you can see that the battery life is significantly higher compared to other systems. And in our second semi in the wild user study with 10 participants, each participant participated for 75 minutes, and they were allowed to do any sort of random locomotion in 3 outdoor scenarios that is shown here. And in our leave one participant out benchmark, which is a user-independent evaluation, we observed that the environmental factor does not have any impact on the performance of PoseSonic. Here you see that under a loudspeaker or outside road sidewalk or in a crowded cafe or restaurant, PoseSonic can maintain consistent performance. And here is one more thing that we would like to discuss, that is, there is a slight degradation of performance from the in-lab study to semi-in-the-wild study, that is 6 centimeter to 14 centimeter. It can be attributed to the fact that users were allowed to do any sort of movement in unconstrained scenarios. So if we had a larger data set, definitely the performance would have been better. To evaluate this, just with an additional 15 minutes of data from the new user, we can achieve a mean per joint position error of 11.87 centimeter. Based on the current performance of PoseSonic, we can readily deploy this system in everyday activity recognition, eating detection, or interactive systems. Please stay tuned to follow our new work on this area. For more details, please refer to our paper. Thank you very much. Please feel free to ask any question.
Yeah, thank you very much for this new introduction. Very interesting system. So one question. So, yeah. Speaker privilege. Yeah, okay.
So do you need to take the head-related transfer function into consideration? Head-related transfer function.
Yes, in our semi-in-the-wild study, the users were allowed to move their head freely, and it did not impact our performance that much. But if we want to get a fine-grained movement, I believe probably an IMU on the eyeglass might help more.
Okay, thank you.
Thank you.
Okay.
Yeah, thank you.
So thank you very much. So having gone through 3 different sensing modalities for pose estimation, we now go back to finger tracking. Next paper, abacus gesture, a large set of math-based usable finger counting gesture for mid-air and interaction. I assume